Hello and welcome. In this video we're talking about section 2.5 on continuity. Starting with the definition of continuity, what does it mean to have a function that is continuous at a point? That includes continuous from the left and continuous from the right according to the definition of continuity. And what does it mean for a function to be continuous on an interval? To be continuous on an interval would require that the function is continuous at every number contained within that interval. What are the types of discontinuities? We've already addressed that previously. There are three types of discontinuities that we have seen before: removable, jump, and infinite discontinuities. How can we more precisely discuss the discontinuities within the context of the definition of continuity? Okay, using the definition in order to determine where functions are in fact continuous, that is, on what intervals the functions are continuous. The families and combinations of functions which are continuous, many of the families of functions we discuss from algebra through till now in calculus, many of them are already continuous on their domains, and then combinations of those functions will also be found to be continuous on the domains of the combinations. And finally, the intermediate value theorem, which is a theorem built off of the definition of continuity. So what is the definition of continuity? We might have been first introduced to the notion of a continuous function through its geometric interpretation. Here we are with analytical geometry again. What does it look like to draw a continuous function? We would say, well, if you can draw the function without lifting the pen, that is, draw the entire function without lifting the pen, then you have a continuous function over the interval in which you've drawn it. Now, what does that mean in terms of what we've been talking about with limits? It means quite a bit. It means that for a function to be continuous at an individual point, that is, that you are able to trace the graph of the function straight through a particular point, right? If I were able to draw, sorry about that, get on this layer. Okay, if I were able to draw a continuous curve over an interval, that is, like, pick out a point on this interval, like that point right there. What does it mean that it is continuous at that point in terms of the sketch that I just made? Well, I was able to approach that point from the left. The point itself actually existed and was right where the limit was leading to. Okay? And we're also able to exit off to the right. In other words, the limit from the right also existed, but all three of these had to match. So we require that the limit from the left exists, and by the way, would have to be a finite value. If this limit from the left went off to infinity, we wouldn't be able to find a point to connect it to, because a point can't exist at infinity. So we need the limit from the left to exist and to be finite. We need the limit from the right to exist and to be finite. We need the limit from the left and the limit from the right to equal each other so that the limit overall exists. And we need the function itself to exist at that point, meaning that if we were to input the value of the fixed value a into the function, we want the output of the function to be exactly the same as what the left and right limits were going to. That's the definition of continuity at a point. So how do we determine if a function is continuous at a value such as x is equal to a? Okay, we know from looking at the picture how to know that it is in fact continuous at that point, but how do we do this symbolically? If we're given a symbolic function, if we don't have the graph, and we want to determine is it continuous at some input value, x is equal to a. There's three things we want to check and we want to compare to each other, just as we did geometrically. Check the left-hand limit, that is, as x approaches a from the left of f of x, okay, what does that go to? What is the output? The limit is, and then the limit from the right, you want to check that. What is the limit as x goes to a from the right of f of x? And finally, you want to check what is f of a itself. If all three of these things are equal to each other, then the function is continuous at x is equal to a. Now, this means also, again, that each of these three things have to exist independently, and they must be finite. Again, consider that we had before that the limit from the left and the limit from the right they don't have to be finite by themselves for the limit to exist, right? We can still say the limit is equal to infinity, and we have a meaning for that. or that the limit is negative infinity if each of these are equal to each other, and if they both go to either they're unbounded and large, so infinity, or unbounded and large but negative, so negative infinity. But for this f of a to exist, this requires two things. Okay, it requires that a itself has to be in the domain of f, so you have to be able to evaluate it, right? And it also means that f of a must be finite, because f of a can't equal infinity, for example, right? A function's output is not infinity. We mean something different when we're saying a limit is equal to infinity. The idea there is that when the limit is equal to infinity, recall, is that no matter how large of a number you might choose, the limiting value of the function keeps going higher than that value that you choose. But to say that f of a itself is equal to a limit would require that f of a is specifically a finite number. You can't have the output of a function be equal to infinity. Okay, so we need to check these three things. All three of these have to exist, and they all three have to be finite, and they all three have to match with each other. That's what's going to be required in order to show that something is continuous. Okay. Now, it's also possible to have just continuity from the left and just continuity from the right. Okay? We can say that a function is continuous from the right only if you take the limit as x approaches a from the right of f of x, and it equals the output of the function. And similarly, that the function could be continuous from the left if you take the limit as x approaches a from the left, okay, and you get the output of the function. Okay, what would that look like geometrically? That's always a way for us to interpret these statements, right, to help us to visualize what we're really saying. So what does it mean to be continuous from the right? Well, let's say that we have a graph that has an endpoint on it that we can approach from the right. Okay, but then the endpoint, okay, at that point we do not have necessarily continuity from the left. Now, it could be that the function continues, is still in the domain when we are to the left of this value. Okay, but let's say this is value a, and then let's say maybe I have the function continues off like this or something like that. Okay, this would be an example where the function is continuous from the right. Okay, it's not entirely continuous, of course. It doesn't have the full. It doesn't satisfy the full definition of continuity. Clearly, we have to lift the pen to draw it. But we can say, okay, but this is continuous from the right, because we can approach from the right to some output value, and the output value is exactly, okay, the output of the function is exactly the same as what we are approaching in the limit. So this is continuous from the right. So we can draw this continuously from the right up to and including the point that we are approaching. Continuous from the left is the same story in the other direction. So say we have a function that is approaching from the left some value, some specific point, and that point itself actually exists right where we would hope that it would be. Okay, so the limit, okay, we are approaching, okay, the actual point at A. And we're only approaching it from the left. But we would not be approaching it from the right. Otherwise, if we were approaching it from the right as well, we would just say continuous, as opposed to establishing it was only continuous from the left. Okay? So this could exist and going off to the right, but it doesn't have to exist out there at all. Okay? So this allows for us to have continuity at an endpoint, and the endpoint must be included in order for continuity to be true, right? In other words, the output of the function at A has to exist, and it must be exactly where the limit was going to. Now, again, a function is continuous on an interval if the function is continuous at every number in the interval. So to be asked, is this function continuous on some given interval, you would really need to check every single value within that interval, okay, which there's an infinite amount of numbers densely collected on any interval of real numbers. So we wouldn't be able to do this one value at a time. So instead, we can consider, again, using the underlying geometry of a lot of the families of functions that we've already described through algebra and pre-calculus and trigonometry, for example. Like we know that all the polynomial functions, those are continuous over all real numbers. We learned that when we're starting to graph polynomial functions and analyze them deeply by virtue of their graphs. All polynomials exist over a domain of all real numbers, from negative infinity to positive infinity. So, therefore, okay, they're nice and smooth and continuous. We know from their graphs that is. And so, the polynomials are therefore continuous over their entire domain. Rational functions also are continuous on their domain. Recall that rational functions are ratios of polynomials, a polynomial divided by another polynomial. The only discontinuities we would find in a rational function would be where the denominator equals 0. But if the denominator is equal to 0, then the rational function itself is not defined there. So any value where the denominator is 0 is a number which is not in the domain of the rational. So to say that a rational function is continuous on its domain is okay. Any value that you would exclude from the domain of a rational is going to be a place where the rational itself would not be continuous. We know that from looking at their graphs. Right? So we'll take a look at some families, okay? The different families that we have of functions and where they are continuous, right? So polynomial functions, nice and smooth, right? Things like this, etc., right? On all real numbers. Rational functions, right? We might have, ones with vertical asymptotes in them, for example, right? And so say this is the function like y equals 1 over x, okay? And let's say we have a vertical asymptote at x is equal to 0. Well, then the domain of this function is that x is not equal to 0. And the rational function is then continuous on its domain. So this would be continuous on the intervals negative infinity to 0, open, union, 0 to infinity. That's its domain. Okay. Roots and radicals, those are also going to be continuous on their domains. Now, if you have a square root function, called a square root function, look like something like this, right? It has an end point. Okay. The domain of the square root function would be closed interval from 0 to infinity, and then we can say that the square root function is continuous on that interval from 0 to infinity. And we are implying, because there is a closed interval here, notice from the geometry of the graph, this implies, when we say this, that it is only continuous from the right at x is equal to 0, because that is an endpoint of the domain. Any other point that we choose within the domain of the square root function, let's say I just choose an arbitrary point out here, notice that that point is exactly equal to the limit as we approach from the left and from the right towards that point. Right? So it's fully continuous at any point within the open interval interior of the domain. That is open 0 to infinity, it is fully continuous there, but on the left and the right. But at the end point, right, at the end point itself, we would actually be continuous only from one side. In this case, it would be continuous from the right. Okay, now the odd root functions, by the way, the odd root functions have a domain of all real numbers. You take something like a cube root function, all right, something like that, a cube root function, which also looks very, very similar to an inverse trigonometric function we also know. But this would be the function y equals the cube root of x. Okay, or maybe a fifth root of x. A cube root of x might look, more like a square root in this direction, but then sort of through a rotation we have a segment that goes off in this direction as well. All right, so this might be the cube root of x function. The domain of the cube root of x, negative infinity to positive infinity, and the function is therefore continuous on the interval from negative infinity to positive infinity as well. The trigonometric functions, we recall their graphs as well. The sine and cosine functions are continuous on negative infinity to positive infinity. However, the other four trigonometric functions, by virtue of their graphs certainly, the tangent, the cotangent, the secant, and the cosecant. They all have vertical asymptotes, so they all would have infinite discontinuities in them. But the domains of those functions, within the domains themselves, similar to the rational function, when you're within the domain of a trigonometric function, the functions will be continuous on their own domains. Okay. Now, when we're going to want to find where are combinations, let's say, of functions here, where would the combinations be continuous? If we were to put a combination together that included a polynomial piece, let's say, and a trigonometric piece, along with maybe a rational piece or something like that, any combination that we might create of these, ultimately, as long as it's built up out of these fundamental functions here, to say where is a combination continuous is the same as saying what is the domain of this combination. And we'll take a look at a couple examples like that. The inverse trigonometric functions as well, continuous on their domains. An example of an inverse trigonometric function, like the arctangent function. Y equals the arctangent of x. You may recall that the arctangent function is designed off of taking the principal branch of the tangent function from negative pi over 2 to pi over 2, and then switching the input and the output. So whereas the tangent function, right, the tangent function would look like this on its principal wave, and then it would have asymptotes, okay, and then it would repeat, right? If we just take the principal branch of our tangent function, this one right here, okay, and we invert it, we would get this, okay, and it's possible that this might have been the first graph you were introduced to that had not one, but two horizontal asymptotes. Had a horizontal asymptote at y equals pi over 2, and another one at y equals negative pi over 2. But the function, the arctangent function is continuous on its domain. Its domain is negative infinity to positive infinity. It's the range that is restricted here. But the domain is negative infinity to positive infinity, and it is continuous on its own domain as well. Okay. The exponential functions, such as growth and decay functions, we're talking about real values, so with real numbers. So we have, for instance, y is equal to a to the x, okay, where a is greater than 1, that is exponential growth. And we also have y is equal to a to the x, right, where a is between 0 and 1. Okay, it's exponential decay. Both of those, again, continuous on their domains. The domain of the exponential functions, negative infinity to positive infinity, okay, negative infinity to positive infinity, and therefore they are continuous from negative infinity to positive infinity. And the logarithmic functions, okay, so we have, for instance, we would have the natural log of x, or log base b of x for any b that could have been a base of an exponential over here. Remember that these had horizontal asymptotes on them, by the way. Right? Remember that these both have horizontal asymptotes at y is equal to 0. Well, the inverse of that, the logarithm, has a vertical asymptote at x is equal to 0, and then the graphs of these functions would look like this. Okay, this is the inverse of the exponential growth function. Okay, the other logarithmic function, the inverse of the decay model, would be like something more like this. Okay, again with a vertical asymptote at x is equal to 0. In either case, for the logarithmic functions, we have the domain is, oh, sorry about that. We'll get to that there. The domain of these logarithmic functions is that x is greater than 0, or I'll put that on an interval, right? Open from 0 to infinity. And we can see from their graphs, they are also continuous on those open intervals from 0 to infinity. Draw a line here to sort of separate this from talking about combinations. We'll make in a moment, okay? So this is to say that if you have any functions from these basic families that we should be pretty well familiar with through our study in algebra and pre-calculus, the families of these functions, okay, are continuous at every number in their domains. So if you know the domain of the function or the combination of these functions that you have, then you also know where it is going to be continuous. Let's take a look at an exercise. We'll move ahead. Okay. Here's given a graph, where we're not told what the symbolic form of this function is, but just given the graph, state the intervals on which the function is continuous, and also state each type of discontinuity encountered on the graph. Recall that we've talked about discontinuities in this course, 3 types of discontinuities. I've restated them down here: removable, infinite, and jump discontinuities. Okay, the removable type was the kind that would show up as a hole on the graph. The infinite type of discontinuity, that would be a vertical asymptote. Sorry. All right, the removable type is graphically represented as a hole on the graph. Okay. The infinite discontinuity, that is a vertical asymptote on the graph. And these jump discontinuities, it's a finite jump that we're talking about. Okay. It could be included at the endpoint or not, in order for us to have a jump discontinuity. Let's take a look at this graph and see what we can figure out. So, starting from the left and reading off to the right, notice that at -3, okay, we'll start there. At x is equal to -3, this function is continuous from the right. Okay, right? We can approach this point from the right, and we get exactly that output, that y value, if we were to plug -3 in. Okay, so that is the limit as x approaches -3 from above of f of x is equal to f of -3 itself. We can see that from the graph. Okay. Now, we have nice continuity in general from the left and from the right for any point we choose in this interval here. But then when we get to this hole right here, okay, we got a hole, that's a removable discontinuity. Okay. So we'll name that removable discontinuity, a removable discontinuity at x is equal to -2. Okay. Now, within the context of the definition of continuity, this more precisely means this: the limit of our function as x approaches -2 from the left, that's of f of x, okay, what is that equal to? We can see from the graph, okay, well, we're not given the value, but that is equal to a finite value right here, whatever that is right there, right? But we also see that that's exactly equal to, in this case, that's equal to what the limit of the function is as we approach -2 from the right. Okay, so those two equal each other. And remember, if the limit from the left and the limit from the right both equal each other, then that means the limit overall exists. Okay, so the limit as x approaches -2 of f of x, that exists. Okay, it exists, and it is finite. We can see because it approaches a finite y value here. Okay, but f of -2 itself does not exist at all. In other words, there is no point, there is no closed point for when x is equal to -2. In order to get continuity, we would want f of -2 to equal whatever the y value is at that point, and in that way we could fill in the hole and create a continuous extension of this curve. Now, what if f of does it mean that if you have a removable discontinuity, does that mean that the function does not exist there? That's not necessarily true. That is, that -2 as an input could have output a point with a y value somewhere else, like here. Let's suppose that that point existed. Okay, then the y value for this point right here, if the x value is -2, the y value would be f of -2, right there. So then, in this case, f of -2 would exist, but f of -2 is not equal to what the limit was as the function approached -2. Okay. Now, this is a removable discontinuity right here, right? But a very similar situation whereby the point is not on the curve exists over here, and we should take a look at that as well. But I'm going to continue now from moving from the left to the right, passing this hole. We're going to go onto this piece right here. The function is continuous all along this open interval. It's continuous until this value. Now, this is -2, -3, so that would be -1. Okay. So what do we say is happening at -1? We have another kind of discontinuity approaching a vertical asymptote. That vertical asymptote, okay, is located where we have an infinite discontinuity. Okay? Infinite discontinuity. Infinite discontinuity at x equals -1. Okay, now what happens in terms of the limits there? The limit as x approaches -1 from the left of f of x is equal to -infinity, and the limit as x approaches -1 from the right of f of x is also equal to -infinity, so the limit overall exists as -infinity there, right? In the sense that we've defined an infinite limit. Okay? But the function f of -1 is not defined there, right? So f of -1 itself does not exist. Now, does that mean that anytime there's an infinite discontinuity, that the function itself won't exist? Not necessarily. It could have been that there was another point that existed, maybe all by itself, at some finite y value. Well, that would then allow for -1 to still be within the domain of the function overall, because it does give an output. But that output does not bridge the gap between the two pieces, and there is no value, remember by the definition of what it means for a limit to go to something like -infinity, no matter where we choose to place a point down here to try to bridge the gap, the thing is that this is always going to surpass that point, and it's just going to keep going down. And so we'll never actually be able to create a continuous extension of this function through an infinite discontinuity. I'd like to go back to the hole again and mention that, again, it is possible for us to fill in this hole, to replace the removable discontinuity by redefining the function in such a way where we say, well, let's define the function so that if -2 was the input, that the output would be whatever the y value is at the removable discontinuity. Okay, we'll take a look at doing that in a moment as well. Okay, but we have a vertical asymptote here. Okay, right. We have a vertical asymptote. A vertical asymptote is associated with an infinite discontinuity. Right? All right, an infinite discontinuity. Okay, now beyond the infinite discontinuity at -1, then we pick up again on this piece right here. It is continuous here, and it is continuous right up to that point, and that is a closed point right there where x is 0. Okay, where x is 0. So, for x is equal to 0, the function is continuous from the left. Okay, so let's include that on our list here. At x equals 0, okay, we have f is continuous from the left. Right? So, in other words, the limit as x approaches 0 from the left of f of x is exactly equal to f of 0. The point exists right where the limit is approaching. Okay? But notice it is not continuous from the right at 0. From the right of 0, the limit is approaching a different value, right, than the output there. Okay, so that would be worth noting as well. So note, the limit as x approaches 0 from the right of f of x exists. It is finite. We can see that from the graph. But the limit as x approaches 0 from the right of f of x does not equal what the output of the function is at 0. Right? The limit from the right is approaching this y value, but if you actually plug 0 into the function, you get a different y value. So it's not continuous from the right. However, it is continuous from the left for the point where x is equal to 0. Beyond 0, we do have continuity on this interval here. You can choose any point within here and see that the limit from the left is equal to the limit from the right, which is equal to the value of the point itself. So continuous within this interval here. Then what happens here? Another discontinuity. The limit from the left is finite. The limit from the right is finite. But they don't equal each other. And that's indicative of a jump discontinuity. Right? A jump discontinuity is here. Okay? Of course, the whole, right, noted on the graph here, removable. Okay, removable discontinuity. A infinite discontinuity and a jump discontinuity. Okay, so being a little more clear about our jump discontinuity here happening at 1. Okay, at x equals 1, the function f has a jump discontinuity. That is to say, the limit as x approaches 1 from the left of f of x exists, okay? Right? It exists and it is finite. Right? The limit as x approaches 1 from the right of f of x exists and is finite as well. But right, the limit from the left does not equal the limit from the right for the function. And for that reason, we have a jump discontinuity. Notice that f of 1 itself does actually exist, but it is not on either of these two pieces. So in fact, we can't even say that it is continuous from the left or the right. Okay? So since f of 1, okay, since f of 1 is not equal to either of these one-sided limits, okay, then f is simply not continuous at x is equal to 1. Not in any way. Not from the left, not continuous from the right, not continuous in general. So let's state the intervals on which our function is continuous, starting from the left towards the right. The value at -3, we are continuous. So we'll say we're continuous on the interval starting at -3, so it's closed at -3 because we are continuous from the right there. It's an endpoint of an interval, and we are continuous within the interval towards -3. It's continuous until -2, and at -2 we encounter a removable discontinuity. So we have an open interval on the -2. Right, it was closed on the -3, but open on -2. We jump over the -2 with the use of a union symbol. Pick it up on the other side of -2 until the next discontinuity, which is at -1. So we jump over the infinite discontinuity, right, by opening it at -1. And then we are continuous from -1 until 0. And at 0, we are continuous from the left. So we include 0 with a closed bracket. Then we are continuous within the open interval from 0 to 1. So union open 0 to 1. Okay. I want to make this distinction here that I'm saying that rather than allowing this to just link together, I'm separating these from each other because I want to make the distinction that at 0 itself, it is not just continuous, but in fact I'm saying it's continuous strictly from the left. Okay. Although you might say that if you're including 0 here and then picking it up right to the right of 0, this is a more or less seamless interval right here. I just want to draw attention to the fact that at 0, it is only, in fact, continuous from the left. Okay, and then after the open interval 0 to 1, it then is continuous not at 1, it's continuous in the open interval, or open starting at 1 until 3, and at 3 it's continuous from the left as well. All right, so from 1 to 3. Did I not state that about x is equal to 3? Okay, so at x equals 3, okay, we have that f is continuous from the left. Okay. All right. So a discussion of continuity. We've used the geometry to analyze continuity here. We've looked at the variety of different types of discontinuities, as well as symbolically, how we can clarify when we have the different types of discontinuities. A removable discontinuity is one such that the limit from the left and the right are both equal to each other, and it's a finite value, right? So we are approaching some finite value from both the left and the right, but the function itself outputs a value that is not at the whole, or the function itself does not output a value at all. So it could be that f of a either does not exist, or it could be that f of a is not equal to the limit. Okay, if the location of this, okay, where the coordinates a comma l, right? If the limit was equal to l, right, then either f of a doesn't exist at all, or f of a is equal to some value that is not the same as l. Okay, that would be a removable discontinuity defined symbolically. An infinite discontinuity, that's a vertical asymptote. That means either the limit from the left or the limit from the right is going to infinity or negative infinity, therefore. Okay. And a jump discontinuity, we have that the limit from the left is finite, the limit from the right is finite, and f of a could be defined at either one of these 2 points, or f of a could be defined at a totally different point, right? Or even a totally different point like up here, or f of a doesn't have to be defined at all. Okay, this is what qualifies as a jump discontinuity. The limit from the left exists and is finite, the limit from the right exists and is finite, but the two are not equal to each other. Okay, so then you would find that the general limit, okay, does not exist for a jump discontinuity. All right. So back to families of functions, okay, families of functions, and then combinations, right? We talked about all the families and where they're continuous on their domains, okay? Now combinations of functions which are continuous at x equals a. If you have more than one function that you already know is continuous on some interval, such as its domain, okay, what can you say about, for instance, the sum or the difference of two such functions? Like, what about the continuity of a function such as x squared plus the sine of x, for example? Well, all right, if we had an example like x squared plus the sine of x, well, we know that x squared, okay, x squared is going to be continuous on negative infinity to positive infinity because it is polynomial. We know that the sine of x is also, it turns out, continuous on negative infinity to positive infinity because it is a trigonometric function and its domain, okay, and its domain is negative infinity to positive infinity. Therefore, the combination of the two, x squared plus sine of x, the combination of the two is also going to be continuous on negative infinity to positive infinity. Okay? If you had something like x squared plus the square root of x, well, the square root of x is continuous on the interval from 0 to infinity, 0 being included. Well, then x squared plus the square root of x would be continuous on that same interval as well. In other words, it is the intersection, take the intersection of the intervals of continuity, in this case the domains, the intersection of their domains. If c is a constant, okay, it doesn't change the fact that the function is still going to be continuous. If f is continuous at a, then multiplying f by a constant, like if I say, well, what about 2x squared? Where's that continuous? It's still continuous from negative infinity to positive infinity, even though we've multiplied by 2. What about the product of two functions? Right? What if we took the square root of x times the arctangent of x, for instance, right, as an example? Right? Okay, well, we have that the square root of x, right, that's continuous on 0 to infinity, and the arctangent of x, that's continuous on negative infinity to positive infinity. And then the product of the two, we take the intersection, okay, the intersection of the two, then is continuous on 0 to infinity as well, including the 0. Right? The ratio f over g, just like when we want to find the domain of a ratio of functions, right? We take the intersection of the domain of f with the domain of g, and we consider anywhere where g itself might equal 0. Essentially, once we know the domain of this ratio, if we're dealing with these families right here, which almost exclusively we would be, if we're dealing with anything from these families right here, then this is indistinguishable from a domain question. As long as you're on the domain of your combination, then it is continuous there, because we've stated that these are all continuous within their domains. And also the composition. Now, composition is a little trickier to understand. When we're taking, for instance, the limit, right, which is a requirement for continuity, we have to be able to take the limit of whatever we're looking at in order to establish if it's continuous, the limit as x goes to a. Well, the limit as x goes to a of the composition f of g of x, okay, in order to evaluate that limit, we actually are not, we're not plugging x into the function f. We would be plugging x into the function g. So what we want to be able to do is to pass the limit through the composition in this way. When we're taking the limit as x goes to a of f of g of x, what we want to do is to be able to push the limit inside the parentheses, because g of x is the one that's going to be taking the input x. It is the output of g of x that becomes the input of f. Recall when we do a composition. So it's not that f has to be continuous at a. It's first g has to be continuous at a. That means the limit as x goes to a of g of x must exist, and g of a must be equal to that limit, and whatever g of a is, okay, whatever g of a is, we're then going to want to be able to establish that f is continuous at g of a. Right? So that is that the output of the inner function, is also giving us a value whereby f is continuous. Okay? Here's an example here, okay, symbolically try to describe this. We have here a composition of functions. The outer function, let's say f of x is equal to the sine of x. And the inner function, g of x, is equal to x plus the sine of x. Okay, so then we are looking at f of g of x is equal to the sine of x plus sine of x. It is a composition of two functions. In order for us to run this limit, we want to check to see, can we do this? Can we push the limit into the parentheses to take the limit as x goes to pi of x plus the sine of x? In order for us to be able to do that, what we really need is for the output of this limit to be a value where the outer function is also continuous. Right? So let's let b equal the limit as x approaches pi of x plus the sine of x. That is that I'm choosing b to represent the output of the limit of the inner function. Now we can evaluate that one. Okay, we have a sum of two functions here, right? We have x is polynomial, so x is continuous on negative infinity to positive infinity because it is polynomial. And we have sine of x, it also is continuous on negative infinity to positive infinity because it's a type of trig function, and that's its domain. The domain of the sine function is all real numbers. Therefore, we have the sum of two functions that are continuous on all real numbers. Okay, so I'd say therefore x plus the sine of x is also continuous on negative infinity to positive infinity. So we already know the limit from the left is equal to the limit from the right, which is equal to the value by plugging this in. So we can just plug pi in to this, okay, by continuity. The way we run this limit is we don't have to graph this function. We don't have to plug values in that are close to pi. We know because this is a combination of functions that are continuous on their domain, and we are approaching a value which is entirely within that domain, then we know by continuity then we can simply just plug pi in to the combination. If the function was not continuous at pi, then we would not be allowed to just plug the number in. Okay? By continuity, so by continuity, b is going to equal pi plus the sine of pi. We are able to just plug the value of a into the function to do the limit. And the sine of pi is 0, so pi plus the sine of pi is equal to pi plus 0, which is equal to pi. So here's what we have now. We are not evaluating, not yet, we're not evaluating actually the sine of pi. This is what we're evaluating now. The limit as b approaches pi of the sine of b. Right? So that is, as we plug in values to this combination here, as x is not equal to pi in general, right, but we're very close to pi, either from the left or the right, the output of this function is not exactly equal to b. The actual output is very close to b. Okay? Sorry, the output is not pi, it's very close to pi. That is the output, which I've called b here. So it's not that we're just taking the output of this and plugging it into that function. Remember that plugging into the function to do the limit, that is exactly what continuity tells us we're allowed to do if the function is continuous there. So what we have to check to see is the sine of b continuous at pi? Now, again, now we're dealing with evaluating the sine function, the sine of x, so it's the sine of b. And the sine of x, again, is continuous on its domain, that is negative infinity to positive infinity. Okay? And since pi is contained within that interval, certainly it's a real number, then this is continuous. Okay? All right? Then sine of x is continuous at x equals pi. Therefore, we can evaluate this limit now by just plugging in pi. We verified that this is continuous there. And then this output is 0. Okay, so the limit here, as stated, that limit is equal to 0, therefore. Right? We pushed the limit to the inside. By continuity of the outer function, we were allowed to do that. Then we ran the limit on the inner function. The output of the inner function became the new input of the outer function, as long as the outer function was continuous at that output itself. Now, where might this process create complications? Where might this not work? And it could be where, if the type of limit that we're looking at, okay, we don't get actual continuity, or the type of continuity, okay, that we might have hoped to get. So let me take a look. Take a look at another couple of just quick examples here. Try and come up with one. How about the limit as x approaches pi of the square root of the sine of x? Right. So here we're looking at the outer function f of x is the square root of x, okay, which we know to be continuous on closed from 0 to infinity. That. Okay. And we have the inner function g of x is, well, our sine of x function, and that is continuous on negative infinity to positive infinity. If we were to push the limit onto the inside, the limit as x goes to pi of the sine of x, the inner limit would be okay, because the limit as x approaches pi of the sine of x by continuity is equal to the sine of pi, and the sine of pi is equal to 0. But that does not mean we get necessarily the square root of 0. Okay, this means instead we get the limit. Okay, let's call this b again right here. Now we have the limit as b approaches 0. All right, because it turns out as if x is a little bit less than pi, okay, we'll get an output that's close to 0 but not equal to 0. Let's look at the sine function, right? The sine function, which, looks like this, and of course continues indefinitely back and forth, up and down. Right, here's where we're talking about at pi. if x is chosen to be a little bit less than pi, then we're going to be outputting a value that's a little bit greater than 0. So we would be approaching from above, right? If we're approaching pi from below, then that means we would be approaching 0 from above in the output. But if we were approaching pi from above, right, if we were approaching pi from above, choosing numbers that are just a little more than pi, notice from the graph we expect to get values that are a little bit less than 0 then. Okay? So this limit, okay, this limit is saying that we are also requiring a two-sided limit from both the left and the right for the output as well. This means we would be looking at the limit as b approaches 0 of the square root of b, for example. And remember that this limit itself, this limit does not exist, okay, since the domain is from 0 to infinity. We can't choose b to be less than 0, right? So this limit, again, this limit right here is not simply evaluated by plugging pi into here and taking the square root of the sine of pi, because the square root of sine of pi would just be equal to 0. The problem is that the inner function outputs a value, right, by continuity, but also by continuity we are approaching that output value. We're not actually at that output value, and we need to consider that in the outer function as well. So think about this example right here a little bit when you're trying to figure out what's the issue here with composition. Why can't we just plug the number in and be done? In most cases, for most combinations of functions that we'll be using, in most cases that would be fine to just plug the number in. But there are also cases where that's not necessarily going to be okay. Okay? But let's say that we had the limit as x approaches pi of the square root of the absolute value of the sine of x as one example. Well, now this one, we actually have f of g of h of x, so we have, so we're including another function here, the absolute value function. So we can push the limit as x goes to pi into the square root, okay, of the absolute value of the sine of x. We can push that limit inside of the absolute value as well. So the limit as x goes to pi of the sine of x. Okay. Now, notice that in this case, okay, when you take the limit of sine of x here, you're approaching 0, but then you take the absolute value of that, and you're not just approaching 0 from the left and the right. You're not approaching 0 from above and below. This can't output a positive number. So this is going to give us the limit of b approaching 0 from above automatically, right? Because absolute value will not output a negative quantity. So this will give us the limit as b approaches 0 from above of the square root of b, right? So we started with a two-sided limit absolutely here, but because of the absolute value in here, it transformed it into a one-sided limit that was approaching from the side where this limit itself would actually exist. So the idea here is to determine if this is a combination of functions that are already continuous on their domains, and therefore determine the domain of f of x, if so. And it seems that this is a combination of a few functions here. We have, let's say, function g of x is equal to x squared plus 1, the numerator of the interior of this radical here. And that is polynomial. It is polynomial and is continuous on its domain, negative infinity to positive infinity. And we have the denominator there, h of x. That function, 2 minus x, it is polynomial as well, and therefore it is also continuous, negative infinity to positive infinity. Then we have the ratio, g of x over h of x, x squared plus 1 over 2 minus x. That is a rational function. All right, so we have polynomial. Now we have rational, a ratio of two polynomials. Okay, and it is continuous on its domain because it is rational. So this is continuous on the domain where we would just exclude x is equal to 2. So from negative infinity to 2, union 2 to infinity. And then finally we have this outer function here, the radical. Let's call that k of x. K of x equals the square root of x, continuous on its domain. It is a root function or a radical function. K of x equals the square root of x, and so it is continuous on its domain from 0 to infinity. And of course at 0, okay, it is really, we are saying that it is continuous from the right at x equals 0 by saying it's continuous at an endpoint of its domain. Okay, so f of x is the combination k of g of x over h of x, we could say. It's a composition and it includes a ratio as well. We could even say that like the numerator x squared plus 1 is the sum of x squared and 1, right? We can dig kind of deep here. It's a combination of a whole bunch of things. But all of these things are continuous on their domain, and therefore this complete combination, composition, ratio, sum, difference, this is also going to be continuous on its domain. Okay. So this is continuous on its domain since f is a combination, okay, of functions which are continuous on their domains. Okay, so we need the domain of f of x. Okay, find the domain of f of x. So square root x squared plus 1 over 2 minus x. Okay, we need for the expression x squared plus 1 over 2 minus x to be greater or equal to 0. Solving this non-linear inequality, okay, we find the zeros of the numerator and the zeros of the denominator as boundary values. Should have studied this in a pre-calculus course, possibly even an algebra course as well. Find boundary values of the domain interval. Okay, so we can look at the zeros of the x squared plus 1 and the zeros of 2 minus x. Okay, now x squared plus 1 itself is always greater than 0, since the square of a real number is always non-negative and you're adding 1, so that's always greater than 0, so it's not equal to 0. But 2 minus x is equal to 0 at x is equal to 2. So we have a boundary value at x is equal to 2. So now we can consider intervals around x equals 2. Furthermore, note that x cannot equal 2. Okay, f of 2 itself does not exist, right? So x equals 2 is not within its domain. But what about values that are greater than 2? And what about values that are less than 2 as well? Okay, and we're going to test those values, and we can test those values in this inequality right here, right? So let's choose some test values. Something less than 2, right? For instance. So let's take 0, for instance. And something greater than 2. How about we take 3? Okay, and so we can plug it into x squared plus 1, which is the numerator. We can plug it into 2 minus x, which is the denominator. And then the ratio of the two, let's call that y, and see if that is going to be greater than 0. We know it's not going to equal 0. We already checked to see if this would ever equal 0. We want to see if it's going to be greater than 0. 0 plugged into the numerator would give us 1. Okay, 3 plugged into the numerator, that would give us, what, 10? So, but I want, really, when we're comparing to 0, we only need to know if the output is positive or negative. That would be sufficient. Plugging 0 into x squared plus 1, we get positive. 3 into x squared plus 1, we would also get a positive number, right? But what about 2 minus x? If you plug in 0, 2 minus 0 is 2, and that's a positive number. Now, a positive divided by a positive is positive, so this statement would be true, as long as we're choosing a value of x, all right? As long as we're choosing x is equal to 0. So if we're choosing a value of x that is less than 2, we are within the domain of our function, therefore. Okay, so it's true within this subinterval right here, negative infinity to 2. Now what about if we choose x equals 3, plug it into 2 minus x, we would get a negative number. 2 minus 3 is negative 1. Now a positive divided by a negative, okay, a positive divided by negative, I'm calling this y right now, that would be negative. And that's not greater than 0, so it would be false there. So we are not including values of x that are greater than 2. So we have the domain now. It seems if we choose any value of x that is less than 2, okay, then we are going to be within the domain of this function. So the domain of f is the interval from negative infinity to positive 2, open. And therefore, the function f of x is going to be continuous on that interval, negative infinity to 2. Okay, and that's what we were after. Okay, now let's take a look at a slightly different example, a piecewise example. Determine if the function f of x is continuous at x equals a. Alright, so we'll recall that a function is continuous at a value x is equal to a if the limit as x approaches a of f of x is equal to f of a. So what we need to do here to check to see if function f of x is continuous at x equals 0, okay, we need to check if the limit as x approaches 0 of f of x is equal to f of 0. So we need to check the limit as x approaches 0 from the left of f of x, and then we're also going to have to check the limit as x approaches 0 from the right of f of x, see if those two equal each other, and we have to check out what is f of 0 itself. F of 0 is real quick to determine here. If x equals 0, then f of x equals 4, so f of 0 equals 4. By the way it's defined. The limit as x approaches 0 from the left of f of x, that means x is on this subinterval here, so we are using this piece of the function. So we take the limit as x approaches 0 from the left of the polynomial now, 4 minus 3x squared. Since this is a polynomial, it is continuous on its domain, which is all real numbers. So we can evaluate this limit by just plugging in 0. So we are using continuity in order to evaluate this limit. So that equals 4. Okay, so we plugged in the value 0 because the function was continuous at that value. Okay, so we're using continuity to evaluate the limit. The limit as x goes to 0 from the right of f of x, that means we're on this subinterval, and that means we're within this piece right here. X is approaching 0 from above of the square root of 16 minus x squared over 4 minus x. And we already know that this is defined from 0 to 4 since it was given to us as being defined from 0 to 4. We could establish what the complete domain is of a piece like this, like doing the exercise that we did just above. Okay, but we're given that this is a subset, at least, of the domain of this for this piece of this function. So we are choosing x within this subinterval between 0 and 4, plugging it into here. Okay, since we have a combination of continuous functions and we know the domain for that combination, we can use continuity then. Okay, by continuity of a combination of functions, again, we were given the domain here, so that's why we can expect it to be true. Okay, we can plug in the 0 then, right? So we get the square root of 16 minus 0 squared over 4 minus 0. That equals the square root of 4. But the square root of 4 is equal to 2. And 2 is not equal to 4. Okay? So we have that the limit overall does not exist. The left-hand limit and the right-hand limit do not equal each other. And if the limit doesn't exist, then we can't satisfy the complete definition of continuity. Okay, So since the limit as x goes to 0 of f of x does not exist, okay, then that means that f of x is not continuous at a is equal to 0. Now, continuing on with the same idea of the previous exercise, we can establish values to plug into our piecewise model in general that could make it continuous everywhere, as we understand the definition of continuity. So we have in each of these pieces, since a and b, we take a and b to be real numbers, okay? A and b are going to be real numbers because we're not told otherwise. Then that means, for instance, that the second piece and the third piece, those are each polynomial. And so those are already continuous on their domains, right? These are each polynomials right here. And the first piece, x squared minus 4 over x minus 2, that one is rational. Okay. So each of the pieces are independently continuous on their domains. And we are given subsets of their domains here to build this piecewise function. Now, in order to make it continuous everywhere, okay, we'll note the domain of f is negative infinity to 2, and then it picks up right again at 2 until 3. It's open at 3, and then it includes 3 and goes off to infinity. So the domain of f is all real numbers, negative infinity to positive infinity. Right? Negative infinity to 2, union, closed at 2, open at 3, union, closed at 3, and open at infinity. In other words, the domain is all real numbers. Okay? And the only places, because these combinations are continuous on their entire domains, the only places where f can be discontinuous would be where there's a switch from one piece to another. Okay? So we're going to have to check for continuity at a equals 2 and at a is equal to 3. That is, we should check the limit as x approaches 2 of f of x is equal to f of 2, and we should check the limit as x approaches 3 of f of x is equal to f of 3, and find what values of a and b would be required in order for those statements to be true. Then we would have continuity throughout the entire domain. Alright, so let's start with the limit as x approaches 2, okay, of f of x. Well, that means we should check the limit as x approaches 2 from below, from the left of f of x, and we should check the limit as x approaches 2 from above of f of x, and of course check also what is f of 2. To check the continuity at 3, similarly, we're going to take the limit from the left as x approaches 3 from the left of f of x, and we're going to take the limit from the right as x approaches 3 of f of x, and we're going to check f of 3. We have to verify that all three of those are equivalent for this function. Now, if we take the limit from the left of 2 as x approaches 2 from the left of f of x, that puts us on this piece, x squared minus 4 over x minus 2. Let's start there. The limit as x goes to 2 from the left of f of x is the limit as x approaches 2 from the left of the x squared minus 4 over x minus 2 piece, right? Because x is less than 2 there. Now, this is a rational function. A rational function is continuous on its domain. Okay, so we are, of course, continuous, okay, on the domain negative infinity to 2, union 2 to infinity. And since we are choosing values of x that are less than 2 and not equal to 2, then we are choosing values that are within the domain. Okay, so we can find this limit by continuity, and we know how. If we plug 2 into this, what are we getting? 0 over 0, right? The indeterminate form. So with 0 over 0, we try to remove the discontinuity. So you get x minus 2 times x plus 2 on top, x minus 2 on the bottom. We cancel x minus 2 with x minus 2. Now we're running the limit as x approaches 2 from the left of x plus 2, and that's polynomial. We can evaluate it by continuity, and we would get 4. Okay, so the limit from the left of 2 is equal to 4. Now what's the value of the function at 2 itself? Okay, let's find that out. F of 2. So we're choosing x is equal to 2, which puts us on this middle piece right here. And plugging in 2 for our value of x on that middle piece, we would get a times 2 squared minus b times 2 plus 3. A times 2 squared minus b times 2 plus 3, which simplifies to 4a minus 2b plus 3. And then we want to take the limit as x approaches 2 from the right. So we're going to have to deal with this expression in a moment. That has to equal, notice for continuity at 2, this is going to have to equal to 4. Right? We have to set this expression equal to 4. But that gives us a linear equation with 2 variables. And in order to solve for 2 variables, we should expect to have at least 2 equations to create a system of equations. So if x is now approaching 2 from above, we're on this middle piece here again. Ax squared minus bx plus 3. Ax squared minus bx plus 3. But that is a polynomial. Okay, and so by continuity, on all real numbers, we can just plug 2 in, and we're going to get exactly the same combination we just had here. In other words, this function is continuous from the right at 2. Okay, so what we need is for 4a minus 2b plus 3 to equal 4. Okay, in order to get continuity at a is equal to 2, we're going to have to make this statement true. Now, do the same thing at 3. Do the same thing at 3 then. We want to take the limit from the left as x approaches 3, which would put us on this piece. The limit from the right as x approaches 3, that would put us on this piece. And then f of 3, if we plug 3 into the function itself, that would also put us into this piece right here. Okay. So we have the limit as x approaches 3, right, from the left of f of x. That puts us on this piece. So that would be limit as x approaches 3 from the left of ax squared minus bx plus 3. And that's going to be, well, we can use continuity here again because this is a polynomial. So this is going to be 3 squared is 9, right? So 9a minus 3b plus 3 as x approaches 3 from the left. Okay. Now if x is equal to 3, that's going to put us on this piece, which is polynomial, and that's the same piece we would use if x was greater than 3 as well. All right? So we have the limit as x approaches 3 from above of f of x is the limit as x approaches 3 from above of the expression 2x minus a plus b. 2x minus a plus b. Right? That's polynomial, so we can use continuity. So plugging in x is equal to 3, we get 6 minus a plus b. Okay? And then finally, what is f of 3? Well, f of 3, we would evaluate this expression here. When x is equal to 3, we're going to get 6 minus a plus b again. So in order to get continuity at 3, we need for these expressions to be equal to each other. Okay? So we need 9a minus 3b plus 3 to be equal to 6 minus a plus b. Okay, so we need that statement to be true. So now we have a system of 2 equations. Solve the system, okay? Solve the system for the variables a and b. 4a minus 2b plus 3 equals to 4, and 9a minus 3b plus 3 is equal to 6 minus a plus b. This is a linear system of equations. It would be advantageous to put them both into a standard form. So, write them all in the form, you have your a's and your b's on one side and your constant on the other, and then you can solve the system by the method of your choice, such as substitution, eliminations, or by using a matrix, if you even wanted to do it that way. Okay? Find out the values of a and b, and that'll complete the exercise. Okay, so find the appropriate values of a and b, and you would have a function that is continuous everywhere. So you can try that now. Solve for a, and then solve for b. Okay, so now there's one more thing for us to talk about, a theorem called the intermediate value theorem. That is that you can find a value between two other values that would satisfy the output of a function. And let's analyze this geometrically. It's going to make it a lot easier to determine what is it that's actually happening here. Let's take a look at a picture. Now suppose f is continuous on the closed interval from a to b. Alright, notice that this interval is closed, so we're including a and we're including b. In other words, f of a exists and f of b exists because a and b are both values that can be plugged into f itself. Now also consider that n, let n be a number that is strictly between f of a and f of b. That's the outputs. So it can either be that that f of a is the smaller number and f of b is the bigger number, and that n is between the two, or it could be the reverse, where f of b is the smaller and f of a is the larger, and that n is between those two. That is, we can have either an increasing or a decreasing but continuous function, over an interval. So let's say we have, here's an increasing one, right? So let's say that this is the point a, f of a, and that this is the point b, f of b. The idea is that, if f of b is greater than f of a, f of b is greater than f of a, because it's an increasing function, then n can be some value in between the two. And so, the idea of the intermediate value theorem is, because our function was already told to be continuous on this closed interval, no matter what value n you choose between f of a and f of b, notice that there must be at least one point on the graph, that would have that output. So this point right here, for instance, would have that output n, and let's say that the input would be another number c that is contained between a and b. That is, this is the value c, comma n, where f of c is equal to n. Now, this doesn't have to be the only place where we have that value. We could have a function that goes up and down and up and down and up and down, right? We can have that this is f of a down here, and this is f of b up here, and it could be that when we choose a value of n, we could have multiple points, multiple points within the open interval from a to b. Right, so if this is a right here, right, if this is a right here and this is b right here, then we are in the open interval from a to b when we're saying we are between a and b, strictly between them. It's possible we could have multiple values of c. So this could be like c1, c2, c3, c4, c5. You could have more than one value of c that would output it. What the intermediate value theorem says is that if we have a function that is continuous on a closed interval, then we know for sure that any number between the outputs at a and b, any number we choose, by continuity, we would have to go through that number at least one time somewhere on the function. If the function happened to be a decreasing function, it still would be true. If it were decreasing, that would be this case right here, where, again, this is where the input is a, but now if we have f of a is up here, but f of b is down here, well, then n would be chosen in this fashion, where f of a is larger, but f of b is smaller. It would still be the case that no matter what value of n we choose between these two, there is going to have to be some point on the curve, at least one point on the curve. It could be multiple points again, at least one point on the curve, right, such that there is some value c that is between a and b, somewhere in this open interval there would have to be at least one value of c such that the output would be n. Okay? This has to be true by continuity on the closed interval. So let's take a look at this example. Use the intermediate value theorem to show there is a solution to the equation natural log of x equals x minus root x in the interval 2 to 3. We're not being asked to find the solution to this equation. We're being asked to show that it exists. And the intermediate value theorem does that for us. The intermediate value theorem can tell us when a solution must exist on a closed interval, okay, if we have a function that is continuous on that closed interval. Now, this equation is not already designed as a function. So the first step here, okay, is to build a function, okay, build a function that represents the equation. And one way we can do that is we can set the equation equal to a constant, set it equal to 0. So the same equation can be written this way. Natural log of x minus x plus the square root of x is equal to 0. Alright, I've just moved everything to one side. It's still the same equation. The solutions to this equation would be the same as the solutions to this equation. And now let's call this left-hand side f of x. We have now built a function, okay, that represents the equation. Okay, so now we have an output of our function f of x we've built. Okay, we have the output happens to be equal to 0. Okay, by the way we've designed this equation. Okay, is the function f of x continuous on our closed interval? That's the first question we have, because in order to use the intermediate value theorem, our function must be continuous. Okay, well, the function is built up out of a sum and a difference, okay, of 3 different pieces. We have the natural log of x. The natural log of x is continuous on the interval from 0 to infinity. Okay, and that includes the closed interval 2 to 3. Okay, so therefore the natural log of x is certainly continuous on the interval from 2 to 3. Right? That is within its domain. We have x is polynomial, and x is continuous on negative infinity to positive infinity. So that's certainly continuous from 2 to 3 on that interval. And the square root of x, well, that one is continuous on the interval from 0 to infinity. Remember, that's continuous from the right. Okay, but again, the interval we're interested in, the closed interval from 2 to 3, is contained within all of these 3 intervals. Okay, so f of x is continuous on the closed interval from 2 to 3, since it is a combination of functions that are also continuous there. So we do have a continuous function. Now what else do we need? If our continuous function, if we evaluate it at the left endpoint of that interval and the right endpoint of that interval, a continuous function, right? Then we know that any value in between those two outputs would have to exist, whether it was increasing or whether it was decreasing or otherwise. Okay, so now check to see what is f of a. In this case, the interval from 2 to 3, a would be 2. So what is f of 2? And f of 2 is going to be the natural log of 2 minus 2 plus the square root of 2. We can find out what that equals. And also check out what f of 3 is. So we're checking f of b. That would be on the other end point. That would be the natural log of 3 minus 3 plus the square root of 3. Let's find out what those are equal to. Okay, so using the scientific calculator, we get that f of 2, natural log of 2 minus 2 plus root 2, okay, is approximately, let's see, 0.10736, and it goes on from there. So we got 5 decimal places. And f of 3, the natural log of 3 minus 3 plus the square root of 3, that comes out to negative 0.16934 if I round it to 5 decimal places. Now, we have that f of 2, then f of 2 is greater than 0. We get a positive number, but f of 3 is less than 0. That's a negative number. Okay, so we know that our function, when evaluated at 2, would output some kind of a positive quantity, f of 2. And we know that our function, when we input 3, is going to output some negative quantity. Okay? So we also know that our function is continuous. Whether our function were to do all kinds of stuff like this, or whether our function would just connect these in a nice smooth curve, right? Or however it happens, by continuity alone, it must be that our function is going to cross 0. So if we choose 0 as the value for n, if n is equal to 0 in this case, we know by continuity and the fact that we had 1 point above and 1 point below our boundary, we know that we're going to have to cross through here in at least one location. Okay, so we can state by the intermediate value theorem, okay, since f of 2, okay, is greater than 0 and f of 3 is less than 0, and of course since f of x is continuous on the closed interval 2 to 3, okay, then that means there must be a number c such that f of c is equal to 0. And if f of c is equal to 0, so i.e. the equation natural log of x, okay, minus x plus the square root of x is equal to 0, okay, must therefore have a solution, at least one solution, okay, contained within the open interval from 2 to 3, okay. Therefore, the original equation natural log of x is equal to x minus the square root of x must have a solution, at least one solution, in the interval from 2 to 3. Okay, and that's the conclusion we reach here by use of the intermediate value theorem. So this is supported by the underlying geometry of continuity to help us to visualize why this must be the case. So that's it for this section. Okay, try it out in the homework and let me know if you have any questions. Take care.